Our objective in this lesson is to differentiate a function with rational exponents. Basically, we just use the power rule for rational exponents. If y equals x to the p over q, where p over q is a rational number, then y prime, the derivative with respect to x, of x to the p over q, equals p over q times x to the p over q minus 1. Remember how our power rule works? Take the exponent, p over q gets multiplied to the front, and then we subtract 1 from the exponent. This can be proven using implicit differentiation. If we take our equation, y equals x to the p over q, and raise both sides to the q power so that we don't have rational exponents, we get y to the q equals x to the p. Now we can take the derivative implicitly of both sides using what we use normally without the rational exponents. So the derivative with respect to x of the left side, y to the q, equals the derivative with respect to x of the right side, x to the p. Using my power rule, I get q times y to the q minus 1 times dy dx, using my chain rule, equals the derivative p times x to the p minus 1. Now I divide by the stuff dy dx is multiplied by to get dy dx by itself. So I have p times x to the p minus 1 over q times y to the q minus 1. Now, of course, we don't have to write this as y because y is equal to something that has x in it. So we'll rewrite that part as x to the p over q and include all the other parts around that. P over q times x to the p minus 1 in the numerator and the y to the q minus 1 in the denominator. Now I'm going to distribute p over q to simplify that, and we get p over q times x to the p minus 1 over x, p over q times q is p, minus p over q times 1 is p over q. That equals p over q times, these bases are the same, and I'm dividing, so I subtract exponents, p minus 1 minus p over q. Notice p minus p is gone, and the negative of negative p over q, we're left with x to the positive p over q minus 1. And that's exactly what our power rule shows us. Isn't that neat? Examples. Find the derivative of each function. Now this is a radical. H of x equals square root of x, but it can be rewritten with a rational exponent, x to the 1/2. Now we use our power rule for rational exponents. H prime of x, 1/2 multiplies in front, and subtract 1 from the exponent, 1/2 minus 1, or negative 1/2. Now this can be better written as 1 over 2x to the 1/2, but better yet, because the question was given with a radical, we give the answer with a radical. H prime of x equals 1 over 2 square roots of x. F of x equals 1 over 2 times the 5th root of x squared. This one also requires being rewritten first. So we'll say f of x equals 1/2, constant multiple. This is x to the 2/5. I'm going to bring it up to the numerator, x to the negative 2/5. Now I can use my power rule for rational exponents. F prime of x equals 1/2, the constant multiple, times, multiply by the exponent, negative 2/5, and then subtract 1 from the exponent, negative 7/5. Negative 2/5 minus 5/5 is what we're doing. Negative 2/5 minus 1, and 1 is 5/5. Now I can clean this up a bit. 1/2 times negative 2/5, 2 divided by 2 simplifies, negative 1 fifth times 1 over x to the 7/5. And again, because my original problem had a radical in it, I'll give my answer with a radical in it. Negative 1 over 5. The denominator of the rational exponent means the root. So this is the 5th root of x to the 7th. And there we have our derivative. Y equals tangent theta to the negative 3/4. Let's find our derivative, dy d theta. I notice I have a composite function. There's an inside here. So I do my outside derivative first, which is using the power rule. Multiply by negative 3/4. The inside stays the same. Subtract 1 from the exponent is subtracting 4/4. That makes negative 7/4. Now I multiply by the inside derivative. Derivative of tangent theta is secant squared theta. I have a derivative, but I can clean this up a bit. Such as negative exponents, I can put those back in the denominator. So what's left in the numerator? Negative 3 secant squared theta over 4 tangent theta to the 7/4. Find the points, if any, where g of x equals 3 minus cubed root of x has any vertical tangent lines. Well, when a function has a vertical tangent line, we know the derivative doesn't exist because the slope of a vertical line is undefined. So let's make that note. The slope is undefined. The derivative does not exist. Let's start by then finding the derivative of this. Well, of course, we have to rewrite g of x, so it says 3 minus x to the 1/3 has a rational exponent. Therefore, the derivative g prime of x equals the derivative of 3 is 0. The derivative of x to the 1/3 is 1/3. X subtract 3/3 makes negative 2/3. So my derivative is negative 1 over 3x to the 2/3. Now, this is my derivative. Where does something not exist? In this case, it's where the denominator equals 0. Just the denominator. So I'll rewrite 3x to the 2/3 by itself equals 0. I can divide by 3 and get x to the 2/3 equals 0, and then I can raise both sides to the reciprocal exponent 3/2 and get x equals 0. So there is a point where g of x has a vertical tangent line. It's at x equals 0. But of course I also need the y coordinate. So after this, I plug it in to the original function and get 3 minus cubed root of 0, which is 3 minus 0, or just 3. So the point is 0, 3. Thanks for watching.